Hello everyone. So there's a few things we should talk about that are related to section 6.2. And one of them is a question that comes up sometimes, and the question is why do we even need these z-scores? So one of the reasons that z-scores are nice, other than the fact that it's a way of standardizing every normal distribution, is you can get information from a z-score that you can't really get otherwise. So as an example, this is an example I use quite a bit. If you have a friend who is studying the distribution of weights of field mice, so maybe this person is trying to figure out if after some sort of natural disaster, if there was any effect on the local wildlife, and maybe they are studying the weights of field mice, and they may say to you something like, "You're not going to believe this mouse I found. This mouse weighed 1.6 ounces, this field mouse." So if you have no idea about the weights of field mice, like most people wouldn't, anybody who doesn't study them wouldn't really know, so you might be like, "Oh my God, was he starving?" And your friend's like, "No, he was way overweight." So there's really saying that a mouse weighs 1.6 ounces to someone who doesn't know about mice doesn't give a lot of information. But if this person said to you, and you understood z-scores, and this person said to you, this mouse had a z-score, this mouse weight had a z-score of 3.2. Well, immediately you're going to know that that's a huge mouse. That's an outlier. Remember, the outlier is plus or minus 2.5. So if you have a z-score of 2.5 or more, or negative 2.5 or less, meaning a larger negative, that's considered an outlier. So a z-score of 3.2 is a very big mouse. And remember that some z-scores, like the example we used in the video, I think we had a Pistons basketball player who was 7 feet tall and had a z-score of 5.25. So when you get z-scores beyond 3, you're in kind of rare territory. And like an extreme z-score of roughly 5 is so rare, it would be like finding, just crossing paths with somebody just in your average day of who's 7 feet tall. So the z-score gives that, it works on all data. So not only for field mice, but for anything really. If you know the z-score of a data point, you have quite a bit of information about that data point. As far as considering that the data follows a normal distribution. If the data follow a normal distribution, meaning that if you line up all the data on a number line, so here's a number line, and if you take measurements of all these things that you're talking about, and let's just say we did some kind of dot plot, and if you notice that over time, your measurements are following this sort of bell-shaped curve, and so much so that it actually follows a normal distribution, well then you can use these z-scores. So if you run across a data point with a z-score of, say, -4, you know that is a really unusually small data point. So that's one of the big advantages of z-scores. It just standardizes everything so that we can have conversations really about data that we don't have any intuition about. As long as we're using a z-score, we can make some sense of it. Another thing we need to take a look at is the Chapter 6 handout. So this is in the handouts folder in Blackboard if you haven't printed it out yet. And what this shows is some formulas. So we've got the converter from a raw data point to a z-score, and this one we use quite a bit. Then this is the other version of it. So if you have a z-score and you want the raw data or the actual x value, use this one. We've got a couple commands. Now, in section 6.2, we looked at this normal CDF, a lower bound, upper bound, and then these two commands, these two inputs, which are optional. If you don't put anything here, it assumes that you're using a standard normal distribution. So it assumes that the mean is 0 and the standard deviation is 1. And then this one we'll look at soon, the inverse norm, which is sort of the opposite of this. So we'll look at this one soon. And then at the end of chapter 6, 6.4 and 6.5, we will look at the sampling distribution for x bar. So I'm sure I'll mention this again when we go over this section. And then this p hat is introduced in our book in chapter 6, but we don't actually use it till chapter 7. So I included it here because it's still a sampling distribution, and the topic of sampling distributions, that topic is introduced in chapter 6. So I put this for the chapter 6 handout, but we'll look at this right at the beginning of chapter 7. So anyway, this is a handout you'll probably want to have with you when you're working on your homework, especially towards the end of chapter 6. And then there are a couple other handouts we need to take a look at. So there are a couple of handouts that are called section 6.2 addendum that are in Blackboard under the lecture notes tab. And this one is about probability distributions. And this is it's going to explain the difference between a discrete distribution, like in chapter 5, and continuous distributions, like we'll see in chapter 6 and beyond. So this one talks about probability distributions. Remember, all these is they show how the probabilities of various events are distributed. And it shows how likely these events are. So we talked about probability distribution tables in chapter 5, and then we'd take that table and convert it to a graph like we did in chapter 5. So that's what we're talking about. So a probability distribution is just an assignment of probabilities to each distinct value of a discrete random variable. So remember, when you have a discrete random variable, you can talk about each distinct value. And that would be like if we were going to flip a coin 3 times and count the number of heads. So it could be anywhere from 0 to 3, and we would assign probabilities for each of these. And we would find those either in the table or using binomial PDF like we did in chapter 5. So if you have a discrete probability distribution, you have these distinct values like 0, 1, 2, and 3. Okay, but when you switch over to a continuous random variable, well, then it's not so simple. Continuous random variable could be like the air pressure in your tire in pounds per square inch. And the air pressure in a tire is not going to either be only 32 or 33. It could be any of the infinite number of values in between here, limited only by the precision of your measuring tool, right? So for a continuous random variable, a table won't work. We can't use a table. And for a continuous random variable, we don't have distinct values. We use interval of values. So because of this difference, distinct values where we can just use arithmetic to sum these, to interval of values where we actually need calculus, it's two completely different ways of handling these. So again, we're not going to use calculus because we'll use in the long ago, not real long ago, but we would use tables, but now in modern times we use a calculator. But these values come from calculus. Somebody had to use calculus to come up with that original table of values. But okay, so a probability distribution of a discrete random variable, so we're talking about discrete again, like chapter 5, could be given in the form of a function, like, for instance, binomial PDF, right, or binomial CDF. So we don't need to know this, but it's called a probability mass function. You'll maybe see that word if you take another stats class. But so it could be a function, a table, or a histogram. And remember, a histogram is really just a graph of the table, right? A histogram is just the graph, the probability distribution graph of the values from the table, but our book calls it a histogram. And the table lists all the possible values that the random variable can assume, just like it does here, right? If we're going to flip a coin 3 times and count the number of heads, you can only get 0 through 3. And then we would have calculated the probabilities. And the histogram displays this information graphically, right? The histogram is just a graph of the table. Okay, so now we're switching though. So this, what we were just talking about, was a discrete random variable. Now we're switching to continuous. And we really don't go back. Once we go to continuous in chapter 6, we pretty much stay with continuous. So probability distribution, or a curve, of a continuous random variable is given in the form of a function. Okay, so the function that we're using is normal CDF right now. We'll see other ones later. Normal CDF, remember it's not normal PDF. We're never going to use a PDF function for continuous. And that'll make sense when we talk about it down here. So this function will have a domain that coincides with the interval of values taken by the random variable. So it's going to be an interval of values. So that's why we don't have PDF. Right here with a discrete random variable, you have an individual value like 1. When you have continuous, there's no such thing as an individual data point that's going to correspond to a particular probability. It's going to be an interval of values. And again, you'll see why when we talk down here. So for continuous probability distributions, the probability is always calculated for an interval, like we said, for an interval, not for an individual value, but an interval of values. And the probability that a continuous random variable assumes a single value is always 0. This means that for continuous random variables, all of these are the same. So if you look at these, you'll see that if we were talking about a discrete case, these are totally separate. But when it's continuous, they're all the same. What this means is I can put the equal sign here or not. All these are exactly the same. So just to review again, for a discrete, if we're talking about a discrete random variable, we're talking about coin flips, and I say what's the probability that we get less than 2 heads, or I say the probability we get less than or equal to 2 heads. If this is discrete, these are two totally different things, right? For discrete, less than 2 means 0 or 1. Less than or equal to 2 means 0, 1, or 2. So these are absolutely not equal. But with continuous, they are equal. And I'm going to explain it here. If you've had calculus, this will make more sense. If you haven't had calculus, it won't make a lot of sense, but it'll still, I think you'll be okay with it. So in calculus, you'll find the area under a curve. And the way you do that is the intuition that we use is this. We think of, well, I know of a formula from geometry for the area of a rectangle. And since I don't have a formula from geometry for the area under this weird curve, what I'm going to do is break up this area into a whole bunch of rectangles and add up the areas of these rectangles. But when you do that, there's this little error here, right? If I take the area of this rectangle and use it to approximate the area under this curve between this point and that point, this little red area here is an error. And my approximation is going to be too big. So in calculus, what we do is we make this super skinny. And we use a value of a limit so that our rectangle, instead of having a width like this, it's going to be so skinny. Let me get this out of here a second. It's going to be so skinny that it's going to be like this. And think of this as a point, a single point. Now everybody remembers from geometry class, or most of you remember, talk about a point in space. So we've got this point in space. Well, it's kind of a concept, right? Like, what is the area of this point? And in geometry, learn the area of the point is 0, right? It's infinitesimally small. The area is 0. So think of this right here. This is a point on the real number line. The area is 0. So if you think of this, the length of this point, it's also going to be 0. And then we're going to use a rectangle defined by that length of 0. So again, it will make more sense if you've had calculus because you'll be familiar with using limits. If you haven't had calculus, just think of it this way. What's the area of a point? 0. So if you use that point for the thickness of this super skinny rectangle, well, then that area of the rectangle is going to be 0. So because of that, if you want to figure out the area of underneath this curve, underneath one point and only one point, you're going to get 0. And it's basically to find the area under this entire curve with calculus, we have to integrate this curve between negative infinity and infinity. So if we were going to integrate, again, if you haven't had calculus, don't worry about this, but you'll find out in calculus, like, let's say this point right here is, I don't know, let's just say it's 2. If you integrate between 2 and 2 in calculus for any function, you're going to get 0. Whenever these are the same, you get 0. So because of that, adding a point, see, like if x is greater than or equal to a, or x is just greater than a, adding this point a does nothing. The area under any individual point is 0. Okay, so that's why for a continuous probability distribution, these are all the same. Not true for discrete, but for continuous it is. So if I figure out something, like later on we'll do something like this, we'll say what's the probability that z is less than or equal to 2.1? And if I just say what's the probability that z is less than 2.1, it's exactly the same. It's the same if it's continuous, because for continuous it's always calculated for an interval. And if you ever calculate the area under a curve over one individual point, it's always 0. So if I include 2.1 here, it doesn't change anything. That area is just 0. Okay, so it's not a huge thing. I probably explained it too much, but I was just giving you guys who have had calculus a little bit of a intuition about it. But really the takeaway that we need to know is that these are all the same for a continuous distribution. Adding the equals doesn't change anything. And we know it definitely does change everything for discrete. So we use the probability density function to produce areas that correspond to probabilities. So that's just like normal CDF. That's what we talked about in 6.2 when we were saying that the area under the curve is exactly 1. And also we could talk about probability. So if we have z-scores, we could say what's the probability that your data point has a z-score greater than 2.2. And wherever your 2.2 is along here, if this were a standardized normal curve, then it would correspond to the area under the curve to the right of 2.2. Okay, so just think of areas are going to have a one-to-one correspondence with probabilities. And this will all make sense when you feel comfortable with section 6.2, and then 6.3 is going to be applied problems. And so it'll as long as you stay on top of the homework, it's really won't be too much of a problem. Just gonna you just have to be able to shift your thinking a little from discrete distributions to continuous. And then just some mentionings here of where these are used, but really probability distributions are used in pretty much all areas of sciences. Life sciences, social sciences, natural sciences, they're pretty much used everywhere. So, all right, that should hopefully give a little idea about these probability distributions. And then there's one more handout we should look at, which is talks a little about Chebyshevs theorem and compares it to the empirical rule. So earlier in the semester, we talked about Chebyshevs theorem in section 3.2. So here's where I'm going to just make a comparison. This isn't super important, what we're going to do right here, but I just want to show you how Chebyshevs compares to the empirical rule. And the empirical rule, remember, that's just saying that basically 68% of the data will fall within one standard deviation of the mean for any data points that follow a normal distribution. And 95% will fall within 2 standard deviations of the mean. And 99.7% fall within 3 standard deviations of the mean. And that's based on data that follow a normal distribution. So here's the difference between Chebyshevs theorem and the empirical rule, or in other words, Chebyshevs theorem and the normal distribution. So Chebyshevs theorem, the strength of Chebyshevs theorem is that it works with any set of data at all. The distribution of data can have any shape at all. It can be skewed badly. It can be a bell-shaped curve. It could be unknown. Anything at all, Chebyshevs theorem always works. So we talked about this formula here. So the proportion of data that must lie within k standard deviations from the mean is at least this, right? And the ones that we looked at in chapter 3, we only did it for k equals 2, 3, or 4, right? But k could be anything bigger than 1. So these are the ones that we looked at. So basically, we could have some weird data like this. Here's where this could come from. Let's say you today hop in your car, go down to a local daycare, and you just run in the daycare and start measuring everyone in the daycare, write down how tall they are. Well, eventually you're going to get arrested, but if you are allowed to take your data with you while you're in your jail cell, if you plotted out the data, they would probably look something like this. You got a couple of bumps in the data, right? And that'd be because you're measuring heights of a bunch of kids, so they would maybe be around here. There'd be a mean height for the kids, but also there's grown-ups there, right? The ones who are watching the kids, so there'd be another bump here. So looking at this data distribution here, the way these data are spread out, we absolutely cannot use anything from chapter 6 here, because chapter 6, remember, if we use chapter 6, we need our data to follow this bell-shaped curve. They need to be normally distributed. So this is clearly not. So the stuff that we learn in chapter 6 we can't use here, but we can use Chebyshevs. Chebyshevs theorem works on this data, works on this distribution. Should have said this distribution, works on this distribution. It works on everything. So it's nice that it works on everything, but if we know that the data follow this distribution, we can be more precise. See how with the empirical rule, if we know that the data follow a bell-shaped curve, then we could say that 99.7% of the data lie within 3 standard deviations of the mean. So Chebyshevs theorem is less precise, but it works everywhere. So we won't really do much more with Chebyshevs theorem, but I just wanted you just to see it one more time, see how it relates. So Chebyshevs theorem works on everything, but if we know that our data follow a normal distribution, it's better to use chapter 6 techniques because these have been studied extensively and we can make a lot of inferences about the data if we have this situation. Okay. So that's what it says down here. If we have a symmetrical bell-shaped distribution, we can be more precise in describing how the data are distributed about the mean. And then we have the empirical rule here, which we've seen quite a bit in chapter 6, and we'll see a lot of it as we go. This is the empirical rule. It just says that for distributions that follow a bell-shaped curve, which many of them do, we have this layout in the data. And then there's a little application here. I'm not going to ask you to do this. Basically, I just wanted you to see how these two work together, or the differences between them. So we've got Chebyshevs theorem and the empirical rule. and we will use the empirical rule. Well, we used it quite a bit in 6.1, and we're going to use this distribution of data quite a bit extensively in Chapter 6, and we'll use it pretty much for the rest of the semester. We'll be talking about the normal distribution. So anyway, those are just a little extras for section 6.2. Make sure you really practice 6.2 homework. It's super important for us. In 6.3, we're going to get into applications of it, which are a little tricky, but if you're solid on 6.2, they won't be too bad. So keep working, keep asking questions, and I'll talk to you guys soon.